back. We left off the first video talking about effective nuclear charge and how to calculate it. So the big trend is the fact that going across a period, effective nuclear charge increases. And effective nuclear charge stays the same going down a period. All right, so every atom in group 7 will have a plus 7. Every valence electron for an atom in group 7 will have a plus 7 effective nuclear charge. Now let's see some of the things we can do with this. Okay, I should point out that effective nuclear charge is something you actually have to experimentally determine. So the actual effective nuclear charge for lithium is not exactly +1. It's actually 1.28. But this is not something I expect. This is way, way, way beyond the course. So in general, we're just going by the equation we came up with. And in fact, this is just a really fancy way of putting the equation. Z is total positive charge. Sigma is what's known as a shielding constant, which is blah, 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 blah terminology. Shielding constant is number of core electrons. So there's some trends that we've seen. Okay, so let's look at some things. What type of things can we explain using effective nuclear charge? Atomic radius is the first one we're going to talk about, followed by ionization energy. So atomic radius is usually defined as it's hard to define a diameter of one particular atom, but when we have atoms bonded together, we kind of take the center to center distance from one atom to another atom, and we end up calling that, we take 1/2 of that number, this distance, and that ends up giving us atomic radius. It's a better way to do it when atoms are actually bonded to each other. So covalent radius, if we have a covalent compound, it's following exactly the same way. Okay, so let's talk about trends. All right, I'm going to copy our little periodic table over here as we have this discussion. Okay, so here's our friend, the periodic table we came up with. Now, we know what's happening with effective nuclear charge. As we go across the periodic table, the effective nuclear charge is increasing. How do I say this? Effective nuclear charge is going up. So we start from +1 over here, we go to +1, and we go all the way over to +8. So what effect would this have? What effect would effective nuclear charge have on the size of an atom? Well, what we end up finding is, and hopefully you remember this from the periodic table activity, that when we go across the periodic table, the atoms get smaller. And when we go down the periodic table, the atoms get larger. Now, we're going to talk about the smaller trend right now. The smaller one is the best one to explain with effective nuclear charge. So we kind of have to imagine two atoms. Imagine an atom over here where we have an electron on the outside of the atom. This electron out here experiences an effective nuclear charge of +1. And over here, the electron outside on this particular atom, let's say this particular atom, fluorine, will have an effective nuclear charge of +7. So each electron is attracted to the nucleus. Each electron is being pulled towards the nucleus. But which one of these two valence electrons is going to be pulled more strongly towards the nucleus? Here it is, winner, 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 chicken dinner, right over here. This electron, as a result, is going to get pulled much more strongly towards the nucleus, and as a result, instead of the atom being exactly the same size, the atom is going to be smaller, right? So we have the radius of atoms decrease as we go across the periodic table simply because the effective nuclear charge, the pulling power on this valence electron gets larger. It actually pulls the electron in closer to the nucleus. So we don't have same size atoms going across, we have atoms getting smaller. Okay? So how are we doing with that? Pretty good? Now, that's not the same as what happens going down the periodic table. Now, we already know that atoms in the same group have exactly the same effective nuclear charge, but we also know that atoms get much larger. This atom is lithium, sodium, potassium. Potassium is larger than sodium. Sodium is larger than lithium, and for this reason, it's a little bit different. Because effective nuclear charge is staying the same, the reason atoms are actually getting bigger is because they're adding shells. So this atom here has 2 shells, lithium has 2 shells, then atom beneath it, and those are remarkably good circles, I should say. The atom beneath it, sodium, simply has a 3rd shell. So every time you add, well, I don't mean to over-exaggerate it like that, but every time you add a shell, the atom actually gets bigger, okay? So the same rules follow. The next atoms go across, go from largest to smallest going across the table, but they definitely get bigger going down because they get more shells, right? So adding an extra shell makes the atom bigger all the time. So here's kind of a picture of what happens going across the periodic table. Maybe this is going to give us a flashback to our class. So as we go across, remember this entire group has, I don't know why I said group, this entire period has 2 core electrons. So the effective nuclear charge increases from +1 all the way over here to +8, and as a result, these electrons, these atoms actually get smaller. Go down a group, you gain a shell, exactly the same phenomena happens over and over and over. Eventually, you end up with gigantic atoms. Another way to kind of picture the effect of effective nuclear charge is to go across the same, this is period 2 in the periodic table. So every single atom up here has 2 core electrons. And this is actually showing the actual calculated numbers. These are numbers that are slightly different than we came up with. We know lithium is supposed to be +1 and beryllium +2 all the way over to +8. The numbers are slightly different. So imagine, but forget about the numbers right now. We're not actually doing these with computers and calculations. So look at what the sizes or should have been. Lithium is about this big, and fluorine should have about the same exact size. But because the effective nuclear charge increases from +1 to +7, the electrons, the valence electrons, which are outside, are effectively being pulled in much more strongly. So it's a nice kind of way to kind of visualize the effect of increasing effective nuclear charge on the radius of the atom. So here's the typical question you're going to get. Referring only to a periodic table, arrange the elements P, S, and O in order of increasing atomic radius. So let's do that. So we got P, S, and O, and we want to go increasing radius. All right, so it's helpful to kind of put these atoms on the periodic table in the first place. Oxygen is at the very top, and right beneath oxygen is sulfur, and right beneath sulfur is, sorry, I was about to say phosphorus is beneath this. Let me put another atom up here. Nitrogen is right next to oxygen, and beneath nitrogen is phosphorus, okay? So right now we are concerned with these 3 atoms in terms of which one is going to have increasing radius, right? So we're going from small to large radius. Well, we can probably pick out the one with the smallest radius first. And I'm hoping you're going to say oxygen is going to have the smallest radius. Because both of these atoms down here, phosphorus and sulfur, are going down a period, so they all both have one more shell. Okay? So atoms with one more shell can't be as small as, in this case, as oxygen. So oxygen's got to be pretty small. But now we have a choice between phosphorus and sulfur in terms of which one's smaller. Now we assume that phosphorus and sulfur both have this one more shell, but we kind of have to decide which one's going to be smaller. And we know that this group is going to experience an effective nuclear charge of +5. The next group over will experience an effective nuclear charge of +6. So phosphorus, effective nuclear charge of +5, sulfur, effective nuclear charge of +6. So as a result of sulfur having a larger effective nuclear charge, ZF, sulfur should be smaller in size than phosphorus. Okay, so in terms of increasing radius, we should go from oxygen to sulfur to phosphorus. And this is a great test question. They're going to ask you questions about this all the time. Okay, hang in there. Okay, the next trend, the next phenomena we talked about, we actually talked about this at the very beginning of the first lecture when we looked at the concept of ionization energy. Actually, we talked about this in terms of photoelectron spectroscopy, and instead of ionization energy, we looked at the concept called binding energy. which I'm just going to abbreviate right now. Binding energy was how strong an electron was held to the nucleus. Well, we can kind of look at and investigate binding energy in terms of ionization energy. And ionization is just a phenomena where an electron is removed from an atom in a gas phase. So we do exactly the same experiment we talked about in the first lecture. So in case you don't remember, here is our photoelectron spectroscopy experiment, and we shine light. We have a light gun, which we're able to change the wavelength or change the energy from low energy to high energy, shine the light onto the metal, and the metal kicks out electrons. And then we have a detector over here that basically allows us to say, actually, I don't know what this thing is, but a detector allows us to say how many electrons came out. Okay, so we said this was a measure of the binding energy. Well, we can also talk about the energy required to remove the electron as what we call ionization energy, or what I will abbreviate as INRG. Okay? So typically when we perform an experiment to determine what the ionization energy or the binding energy is of an electron, we start with the lowest energy first, and we shine light of the lowest energy on the atom to figure out which electrons get pulled off first. And invariably, it is the valence electrons that get removed first. So we start with, if we're looking at the nucleus of an atom right here, we're going to start pulling away the valence electrons first, and then getting into the core electrons until finally we get to the electrons that are the closest to the nucleus, the inner core electrons, right? So in terms of energy, this requires the least energy. The lowest ionization energies are in the valence electrons, and then ionization energy increases to an absolute maximum when we get to the two electrons that are near the core. Okay. So this is a short graph looking at ionization energies just for the basic atoms in the main group. And these energies are usually the ionization energy is usually in kilojoules per mole. To make things a little bit more complicated, we're not assuming we're talking about one atom, we're talking about a mole of those atoms. So there's an interesting trend. As you go across the periodic table, the ionization energy increases. As we go from lithium to neon, the ionization energy goes through the roof. It's more difficult to remove. Now remember, neon has, if this is the core for neon, neon has 8 valence electrons, and over here, lithium only has 1 valence electron. Lithium has an effective nuclear charge of +1. Neon has an effective nuclear charge of +8. It costs way more energy to remove this 1 electron out here from neon than it does to remove this electron from lithium. Why? Effective nuclear charge. As you go from +1 to a +8, these electrons are being more strongly held, or maybe we want to say more strongly attracted to the nucleus. I spelled it wrong. I'm sorry. Attracted. How about that? These electrons, these valence electrons are being more strongly attracted to the nucleus than this valence electron is for lithium. So as a result, it costs us more energy. On our little electron gun, a light gun that we're shining on our atom, it costs way more energy to remove electrons from here. And this trend is exactly repeated. So the trend of ionization energy loosely follows the trend in radius. And as you go across a period, and again, a period is a row, as you go across a period, the ionization energy increases. As you go down, it's a little bit more complicated. Remember, effective nuclear charge stays the same going down a group. A radius increases. Now, radius increases going down. Radius gets larger going down. Does this make any sense at all? So the radius increases going down a group because we get more shells. All right. Well, think about that in the same token. Ionization energy is how much energy it costs to remove an electron. So why would it be if you look at these two atoms here, hydrogen and cesium, why would it be easier? Why would it cost less? You like my expression here, cost less in energy to remove a cesium valence electron than a hydrogen valence electron? Well, because these electrons are so much farther away from the nucleus. A hydrogen atom compared to a cesium atom is ginormous. The valence electron in cesium is so much farther away than the valence electron in hydrogen. So one thing we can kind of think about this valence electron is being shielded by way more electrons. So even though that has an effective nuclear charge of +1, it's still really far away. So it costs a lot of energy. We see that trend across the periodic table. As we go down everywhere, the ionization energy drops. Now, there is a trend in ionization energy, and we need to kind of spend a moment looking at this. As you go across the periodic table, and this is not just across, but this is literally from hydrogen all the way over to atom number 90. This is what's known as first ionization energy. So this is the very first electron to be removed from the atom. And this is a valence electron being removed. It's never a core electron. And we see an interesting trend. It looks like we start off with going from hydrogen to helium. That's basically going from the top of the periodic table over to helium. Helium has a huge ionization energy. So obviously there's an effective nuclear charge as part of the answer, but there's actually a little bit more. It has to do with how full the valence shell is. Okay? So for an example, take a look at this interesting phenomena going from, I'm a chemistry guy, I have to say interesting phenomena. Interesting phenomena going from lithium to neon. Now, as expected, the ionization energy increases going from lithium to neon because the effective nuclear charge goes from +1 to +8. But there's more going on. You notice these little zigzags in here? What's happening? This is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, chlorine. What's going on? Why is the ionization going up and then dropping, going up and dropping? It has to do with how full the shells are. This atom right here, beryllium has filled the 2s orbital. Right here, this atom right here, beryllium, is filling the 2s. Then we go over to the next atom after boron, lithium, beryllium, boron, carbon, nitrogen. As we go to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Yep, okay, I've got them right. As we go up, so this is lithium, beryllium, boron. How about I just write it in? Boron, oxygen, nitrogen. Boy, did I screw that up. Okay, I fixed it. So this is lithium, and then beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, and then neon. I have no idea why I was getting those mixed up. So we go from +1 effective nuclear charge to +8, and it increases as expected, but we see these little zigzags in here. As we said before, beryllium, the last electron that gets filled in beryllium fills the 2s. And then after we fill the 2s, the ionization energy drops again because boron is doing this. If you look at orbital notation, boron has a 2p electron. It has a 2s that is filled, spin up, spin down, and it's got an electron in the 2p, one electron. As you go closer and closer, carbon, if I change this now to carbon, carbon puts another 2p electron in here. Nitrogen does one better. Nitrogen puts in the third 2p electron. This is very stable. This is not what we've got going on right here is not a completely full orbital, but it is partially full. And a partially full orbital is actually pretty stable and as a result, it costs more in energy to pull this particular electron out of nitrogen than it does to pull the electron out of boron. So we see some interesting phenomena with ionization energy. Obviously, the phenomena is directly related back to effective nuclear charge. As effective nuclear charge goes up, so does ionization energy. So maybe we say ionization energy increases as effective nuclear charge increases. But then the next trend has to do with how full the orbital is. So orbital. A full orbital, whether it's a 1s 2 being fold or a 2s and a 2p being fold, is really stable. Having a full orbital is very stable, but so is having a partially filled orbital. So every place where we have a partially filled orbital, right here with nitrogen, nitrogen has this arrangement with 3 electrons in the peep. So does, right, where are we? Neon, sodium, magnesium, and then 1, 2, 3. So is this atom right here. This atom, if you notice, it peaks again. This is where we have another partially filled orbital. So ionization energy is mostly related to effective nuclear charge, but it also has to do with how full the orbital is. All right. So here's another way to kind of visualize this. So if you have a case where you have an orbital that's filled, let's say you have an s orbital that's filled, two electrons that are paired. This electron right here is really hard to remove. But if this orbital is filled, you only have one electron. This electron here is a whole lot easier to remove now. If you have the orbital partially filled, now this electron becomes hard to remove. But if you have the next electron over, this would be for the atom like oxygen. Now this electron becomes really easy to remove. So the moral of the story is this: filled orbitals, very hard to remove. Partially filled orbitals, hard to remove, okay? Or completely filled orbitals. Like if I had a case like everything was filled, this would be the hardest to remove. If you have a case where you have all 8 valence electrons, that would be a case where they would have the highest ionization energy. You can have multiple ionization energies, right? Yeah, it's possible to remove all of the electrons from an atom. Take an atom like neon, and neon has 10 electrons. The first electron to be removed is one of neon's 8 valence electrons. But then it gets progressively harder and harder and harder. Eventually, you get to the point where energies start spiking. Neon has 6 electrons in a 2p, all right? So 1, 2, 3, 4, 5, 6. After the 6 electrons are removed in the 2p, the energy jumps, because now over here we're starting to remove 2s electrons. So here's the first and the second 2s electrons. After the 2s electrons are done, these are the 1s electrons. These are both of the 1s electrons for neon, and we see the energy just skyrockets. It's a huge amount of energy required to remove these electrons, because if you think about it, neon has 10 protons. The 2 electrons here are not shielded by anything. So the effective nuclear charge on these 2 electrons are going to be plus 10. Positive charge of 10 minus 0. They both have a plus 10 effective nuclear charge. So they're being held on extremely tightly to the nucleus. And it requires enormous energies to remove them. Okay? The type of places where you see atoms completely ionized would be in plasmas. A plasma is technically a gas where the atoms in the gas are completely ionized. The other place you see completely ionized atoms is a place like the sun or stars. Stars are so hot that all the electrons in atoms are kind of stripped away in different portions of stars. Okay, so here's a sample question. Would you expect sodium or magnesium to have a greater first ionization energy? All right, so the first ionization energy is how much energy is required to remove the first valence electron. And sodium and magnesium are right next to each other on the periodic table. So hopefully you remember the trend as you go across the periodic table, the ionization energy increases. And the reason magnesium is going to have a higher first ionization energy is because it is a paired orbital. Um, magnesium has its 3s orbital is filled. So it is going to be very difficult to remove the first electron from magnesium. The first electron from sodium it only has a 3s1, so it's a partially filled. However, the second ionization energy, imagine both atoms have had their first electron removed. Well, magnesium, after it has its first electron removed, is a +1 charge. Now it has a 3s1 electron. Now magnesium, this electron is very easy to remove. I don't know what I'm writing. It looks like I just wrote ear. I'm trying to write easy. But comparatively, after a sodium +1 charge, its electron configuration is now 1s2, 2s2, 2p6. And the next electron to be removed, the second ionization, is going to come from the 2p6, and that is going to be enormous. So in terms of ionization energy 1, magnesium is going to be greater than sodium. But for ionization energy 2, sodium is going to be far greater than magnesium will be. I hope this example helped make sense a little bit. Okay, another periodic trend is what's known as electron affinity, and this is definitely not my favorite trend. It's not the most useful trend to me, but it's basically this. It's the energy released, and then we're talking enthalpy at this point. It's the energy released when an atom in the gas phase accepts an electron. And there are a handful of atoms in the periodic table that like to have electrons, and most of them are in the, if you're looking at a periodic table, they are here. And these are our nonmetals. These are atoms that want to have electrons the most. Most of the atoms over here, obviously our metalloids are kind of in here, but most of the atoms what am I trying to write? Do not want electrons. That's supposed to be a want. So the nonmetals are going to have the largest electron affinities, as we would expect metals. Metals are things that usually want to get rid of electrons. They're going to have very low electron affinities. It's not my favorite periodic trend, but we have to talk about it anyways. So in terms of electron affinity, we tend to see the highest electron affinities towards the right side of the periodic table. So if I had to make a line down here through my nonmetals, the largest electron affinity is going to be here for these elements, because these are my group 7 elements. These are elements that have outer shell valence shell configurations S2 P5. All right, so they have 7 valence electrons. They want the electron the most. All right, so as we would expect, the electron affinity is the highest for group 7, a little bit less for group 6, a little bit less for group 5. But there it is. Okay, so that kind of wraps up our periodic properties, and we have one more thing to talk about. What happens to electron configurations when we make ions? And the idea is when atoms gain or lose electrons, they become ions, and the electrons go in spots that they have a vacancy. So if we start with an atom like sodium, we know that sodium is going to, because sodium's in group 1, it's going to tend to lose one valence electron. If an atom like sodium loses, and by the way, this is the shorthand notation for sodium, the longhand electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. The valence electron for sodium is this electron here on the outside, and if it comes in contact with a nonmetal, this electron's gone. So the electron configuration left over is literally this. So sodium will have an electron configuration. By the way, if you notice, 1s2, 2s2, 2p6 is the electron configuration for neon. When atoms tend to gain or lose electrons, they end up having electron configurations of noble gases. So the sodium +1 ion will have this particular electron configuration. Same thing for nonmetals, like the atom fluorine has a configuration 1s2, 2s2, 2p5. And when fluorine becomes an ion, its configuration will also look like that of neon. It'll become 1s2, 2s2, 2p6. Okay? So there's a lot of this. I mean, you're going to see problems out there where I give you 5 different elements, and they all have exactly the same electron configuration. You kind of have to figure out which one is which element is which. So a problem like this: write electron configurations for the following ions of main group elements. So nitrogen -3. Nitrogen is 1s2, 2s2, 2p3 normally, but if it forms a -3 charge, it means it gained 3 electrons. So instead of 2p3, it's going to become 2p6. That's going to be the n-3 ion. Barium +2. I have no idea what barium is. Let's just skip barium +2. Anything barium +2. Barium is in group 2, so its s2 electrons is going to be gone. So its outer shell electrons will be gone. I just don't have a periodic table in front of me. Beryllium, I happen to know. Beryllium is 1s2, 2s2. So beryllium is in group 2, so it's going to lose these 2 electrons. So when it's done, the beryllium +2 atom is just going to have this electron configuration. Sorry, I'm being sloppy on the barium. I just don't have a periodic table in front of me. Okay, there is an interesting trend when looking at what happens when atoms becomes ions because their radius changes dramatically. In fact, when metal atoms lose electrons, the radius of the ion contracts. So when metals lose electrons, the radius drops phenomenally. Radius, I'm just going to say drops or decreases. So going from a sodium ion, the radius of this ion would be from here to here, but going to the atom, going to an ion, when sodium loses this electron, this 3s1 electron is not here anymore, the atom actually shrinks. So one way to think about this is this valence electron is now gone. The rest of the positive charge basically pulls itself in. So this is a trend you see going across the periodic table as you become an ion, um, as you become a metal ion. Metals, as you go, no, I don't want to say going across the table. Metals tend to shrink when they lose electrons. And if we look at what happens to nonmetals, nonmetals happen to get bigger when they gain electrons. I don't have a good example here, but if a nonmetal gains an electron, we'll have a nonmetal like fluorine will look like this, but the moment it gains an electron, it will actually increase in size. And it's a little bit counterintuitive, but one reason is it actually has this extra electron here. And electrons, imagine fluorine's got these other electrons around it. These electrons will essentially push away because electrons repel each other. So these extra electrons will repel this extra electron that's been gained, and the ion gets bigger. So nonmetals, when nonmetals gain electrons, they get bigger. So this is just a graphic looking at what happens when lithium starts out like this, becomes an ion, gets smaller. Nitrogen, oxygen, fluorine, when they become ions, they get bigger. Now the same trend is observed. We still go from large to small going across the periodic table, right? So nitrogen ion is larger than oxygen ion is larger than fluorine ion. So that trend is still observed. And as well as going down the periodic table, atoms or ions still get bigger going down to the periodic table. There is a term known as isoelectronic series where, hold on. Sorry. How about I just pause? So in isoelectronic series, this is what I was kind of mentioning before. They have exactly the same electron configurations, but very different effective nuclear charges. A good example is oxygen, fluorine, and neon. They all have exactly the same electron configuration of 1s2, 2s2, 2p6, right? But they have very different effective nuclear charges. Oxygen has an effective nuclear charge of +6, fluorine is +7, and neon is +8. So as a result, they all have very different radii. And we know right now that oxygen is going to be much larger than fluorine, is going to be much larger than neon, right? So remember, as atoms gain electron, the atoms, as they gain electron, they get bigger. Okay, so that's it. That is all for our lecture. We're keeping this last half short. I really hope you're okay. Um, Everything is just a little bit surreal out there right now. I really hope you're okay. I know a lot of you work in the medical profession. I hope you're okay. Let me know if you're having any trouble. I'm trying to make this process as easy as possible. I know it's still hard because you have to listen to me talk. If you made it this far in the lecture, then congratulations. Um, but keep at it. All the homework deadlines are extended till the last day of the course, so please keep at it. We do have an exam coming up, but just let me know if you're having trouble, please. All right. Okay. Take care.